Hi everyone, welcome to your lesson on earthquakes. To start us off, we need to just go over a definition of what an earthquake is, and then we'll go into, we'll basically dissect it into all the different layers and the waves and the faults. So earthquakes are just violent shaking of the Earth's crust, and they're caused by movement along a fault, and a fault is any kind of fracture in the Earth's crust. And there are a few different types of faults that we're going to talk about. As the plates move, pressure builds in the rocks, and that pressure that builds up causes them to bend and store energy, and that energy is called elastic energy. I like to use the analogy of a ruler or a yardstick. If you bend it after a certain amount of time, it's eventually going to snap. When it's bent, that energy that's stored up is similar to elastic energy. And so, with the Earth's crust, as it moves along that fault, that fracture in the crust, it builds up energy in the rocks, and when it can't hold anymore, it sort of snaps. And that energy. It's called the elastic rebound hypothesis, which that stored energy becomes too much for the rocks to hold, so the rocks move, and as they move, they release the energy. And when they move and release the energy, that's an earthquake. There's a couple different parts. The foreshocks are the smaller earthquakes that happen before most major earthquakes, and the aftershocks are smaller earthquakes that happen as the materials adjust following a major earthquake. So there's the pre, the during, and then the post. There's three kinds of faults. There's reverse, normal, and strike slip. So if you look at the tree in each of these pictures, it's the same diagram with different things happening to the blocks. With a normal fault, which is the one in the middle, the left block goes down. That is a normal fault when you have two pieces of earth, two pieces of earth, one's going down, one's going up. On the reverse, it's opposite. The left where the tree is going up, and moving down is the right. And then a strike slip is when they go side to side, which is a shearing motion. Normal faults tend to extend the crust, so you can see that the crust is getting longer, whereas reverse faults shorten the crust, they compress. And strike slips move side to side. So, a couple things about earthquakes. The location of the actual movement of rock is called the focus. So the focus is underground, under the Earth's crust, under the surface of the Earth, where the rock actually moved. And then the epicenter is directly above the focus, surface of the Earth. So again, the epicenter is directly above the focus on the surface of the Earth. Focus is where the rocks moved. Epicenter is basically where your earthquake is happening on the surface. So there's different kinds of earthquake waves. So you have this energy built up, the rock moves, and then the movement of the rock create a movement of waves. And that's what causes your destruction. So seismic waves are waves of energy that move through the earth, and there's different types. Primary or P waves are fast-moving waves, and they're first to arrive and to be felt. They compress and expand or push and pull rocks in the direction that the waves travel. And if you type P wave into a Google search, just look at any of the little animations, and we'll look at some in class also when we do our plotting in epicenter. But if you look, they push and pull in the direction that the wave travels. And you can model these with slinkies. The second type of wave is called secondary or S wave. They're slower moving. So P primary, S secondary, second to arrive, and slower. They go side to side. Remember, side to side is another word for that is shear motion. They won't travel through liquids, whereas the P waves can travel through liquids and solids. So when we're looking at the different layers of the earth, that's really important because they will not travel through liquids. That means they cannot go through the outer core. So if we look at this diagram, P waves are the thicker bluish purple line and S waves are the pink line. You can see that the P waves go straight through all layers, whereas the S waves never touch the outer core. And because they can't touch the outer core, they can't go through the inner core either. So P waves are the only type of wave to be able to go through inner or outer core of Earth. Okay, so P waves, again, go back and forth, push and pull, and S waves make like an S shape. They go, I'm sorry, I said P waves back and forth. P waves do not go back and forth. P waves go forward and backward, compress and expand, and S waves go back and forth, side to side, and make a squiggly motion. And the last kind of waves are surface waves. Surface waves, or L waves, because they go lateral, are the last to arrive, but are the most destructive. And surface waves are waves that happen on the Earth's surface. And again, this is when you can actually see the Earth moving. P and S waves you cannot see, like you can see surface waves. Now, we use something called a seismograph to measure earthquakes. And so basically, it's this machine that has a heavy mass that resists motion so that when the earthquake hits, so you see at the bottom, earth motion due to earthquakes, it's either going to go left or right, it's going to go west or east. That pen is going to scribble different directions, different size arrows, and it moves in the direction of the arrow. That's going to tell scientists how close those waves are occurring, what the wavelength is. And if it's occurring really fast, then it means it's So here, this is called, the picture that a seismograph prints out is a seismogram. And the paper moves in the direction, the arrow pointing left. The P wave arrives first. So you see at the bottom is time. So you see the very first little blip in that is where P wave arrives first, and then you have some big waves, and you have a little bit, and then you have a few more big waves, and then at the end you see the surface waves arriving last, and those are really, really tall. So measuring earthquakes, you can measure with magnitude. Magnitude is a measure of the size of the seismic wave produced. So how big is the wave? That's the magnitude. And it's measured on a Richter scale of 1 to 10. Richter uses the largest seismic wave used to determine the rating. So this is the Richter scale, and it goes from 0 to 9 and over. And you can see the difference in different types of earthquakes. 2, hanging objects might swing. 3, comparable to the vibrations of a passing truck. 4, you might have windows break or unstable objects fall. 5, furniture moving, plaster might start falling from walls. 6, damage to well-built structures and severe damage to poorly built ones, etc. So to determine a earthquake location, you look at the difference in arrival times of P and S waves, and that gives you the distance to the epicenter. You need 3 seismic stations needed to find the location of an epicenter, but it's pretty easy using a distance time graph. And when we do our plotting an earthquake, plotting the epicenter paper lab later this week, you'll be able to, you're going to be doing that. So this graph is the P and S wave travel time graph called a distance time graph. You have distance on the x-axis and travel time in minutes on the y-axis. Distance is kilometers from the epicenter. So if you have 3,000 kilometers from the epicenter, because the distance is times 10 to the third power, which means 3 zeros. So we have 3,000 kilometers. You go to the 3 at the bottom and go up to where the P line hits. And you put a little dot there where the P line hits. You see the P line is the bottom curved line. The S line is the top curved line. Those are constant and don't ever change based on how fast they move. So if it's 3,000 miles or 3,000 kilometers away, you want to see the travel time. So if you go up, put a dot, go over, you see the red line goes to a little bit over 5.5 minutes. So that would mean the next P wave would be coming in about 5.5 minutes if it's 3,000 kilometers away. If we go over to 4,000 kilometers away, it is 7 minutes. If we go over to, let's say, 7,000 kilometers away, it goes up to about 10.5 minutes. If we look at the S waves, and we go to 3,000 kilometers away and then go up, it's a little bit over 10 minutes. So in every single situation where you would look at the kilometers on the y-axis, when you compare the P and the S waves, S moves slower, so therefore S is going to have a longer travel time every single time, no matter where you look at it. If we go to 7,000, P is, go over to 7,000, x-axis, go up to where you hit the P and then go over, it's about 10.5, whereas S is 19. So that's how you use the graph. How to use a seismogram is you would just look at the time at the bottom. So you'd see when the first P wave hit, it's at 3 minutes and 3 seconds. And then you would look and see when the next hit, and it's 3 minutes and 9 seconds. And you can count between the difference between 3:03 and 3:09 is 6 minutes. So you can do it that way as well. These aren't very easy to use though, because they're not usually this clear. It's usually pretty hard to tell the difference between the peaks on each of the waves. A tsunami is an after effect of an earthquake. So if you see the focus right there where the fault line is, you see that crust moving up, the right-hand side moving up. That movement of that crust creates that upward wave, which creates a tsunami. And this is some earthquake as well as more earthquake destruction, and tsunami destruction on top of that is oftentimes